In mathematics, a symmetrizable compact operator is a compact operator on a Hilbert space that can be composed with a positive operator with trivial kernel to produce a self-adjoint operator. Such operators arose naturally in the work on integral operators of Hilbert, Korn, Lichtenstein and Marty required to solve elliptic boundary value problems on bounded domains in Euclidean space. Between the late 1940s and early 1960s, the techniques, previously developed as part of classical potential theory, were abstracted within operator theory by various mathematicians, including M. G. Krein, William T. Reid, Peter Lax and Jean Dieudonné. Fredholm theory already implies that any element of the spectrum is an eigenvalue. The main results assert that the spectral theory of these operators is similar to that of compact self-adjoint operators. Any spectral value is real. They form a sequence tending to zero. Any generalized eigenvector is an eigenvector, and the eigenvectors span a dense subspace of the Hilbert space. Discussion. Let H be a Hilbert space. A compact operator K on H is symmetrizable if there is a bounded self-adjoint operator S on H such that S is positive with trivial kernel i.e. Sx x greater than 0 for all non-zero x, and Sk is self-adjoint. Sk equals K S. Display style Sk equals K caret asterisk S. Closing curly bracket. In many applications, S is also compact. The operator S defines a new inner product on H. X, Y, S equals S, X, Y. Display style X, Y underscore S equals Sx, Y. Closing curly bracket. Let Hs be the Hilbert space completion of H with respect to this inner product. The operator K defines a formally self-adjoint operator on the dense subspace H of Hs. As Krein, 1947, and Reid, 1951, noted, the operator has the same operator norm as K. In fact, the self-adjointness condition implies S K N equals K N S. Display style S K caret N equals K caret asterisk caret N S. Closing curly bracket. It follows by induction that if x S equals 1, then K X S pipe 2 N K 2 N X S. Display style KX underscore S caret 2 caret N LEQ K caret 2 caret N X underscore S. Closing curly bracket. Hence K X S lim sup N infinity K S X 2 1 / 2 N equals K. Display style KX underscore S LEQ limbs up underscore N right arrow inf D K S X caret 2 caret 1/2 caret N equals K. If K is only compact. Krein gave an argument, invoking Fredholm theory, to show that K defines a compact operator on Hs. A shorter argument is available if K belongs to a Schatten class. When K is a Hilbert-Schmidt operator, the argument proceeds as follows. Let R be the unique positive square root of S, and for epsilon greater than 0 define A epsilon equals R plus epsilon I minus 1 S K R plus epsilon I minus 1. display style a underscore var epsilon equals r plus var epsilon I caret minus 1 sk r plus var epsilon I caret minus 1 closing curly bracket. These are self-adjoint Hilbert-Schmidt operator on H which are uniformly bounded in the Hilbert-Schmidt norm. A epsilon 2 equals r 2 r plus epsilon I minus 2 k r 2 r plus epsilon I minus 2 k 2 display style a underscore var epsilon underscore 2 caret 2 equals r caret 2 r plus var epsilon I caret minus 2 k r caret 2 r plus var epsilon I caret minus 2 underscore 2 leq k underscore 2 caret 2 closing curly bracket. Since the Hilbert-Schmidt operators form a Hilbert space, there is a subsequence converging weakly to S self-adjoint Hilbert-Schmidt operator A. Since A epsilon r tends to Rk in Hilbert-Schmidt norm, it follows that R k equals A r display style Rk equals R closing curly bracket. Thus if U is the unitary induced by R between Hs and H, then the operator K is induced by the restriction of K corresponds to A on H. U K S U equals A display style UK underscore S U caret asterisk equals A closing curly bracket. The operators K minus lambda I and K asterisk minus lambda I are Fredholm operators of index 0 for lambda does not equal 0. So any spectral value of K a K asterisk is an eigenvalue and the corresponding eigenspaces are finite dimensional. On the other hand, by the special theorem for compact operators, H is the orthogonal direct sum of the eigenspaces of A, all finite dimensional except possibly for the zero eigenspace. Since R equals K asterisk R, the image under R of the lambda eigenspace of A lies in the lambda eigenspace of K asterisk. Similarly, R carries the lambda eigenspace of K into the lambda eigenspace of A. It follows that the eigenvalues of K and K asterisk are all real. Since R is injective and has dense range, it induces isomorphisms between the lambda eigenspaces of A, K and K asterisk. The same is true for generalized eigenvalues, since powers of K minus lambda I and K asterisk minus lambda I are also Fredholm of index 0. Since any generalized lambda eigenvector of A is already an eigenvector, the same is true for K and K asterisk. For lambda equals 0, this argument shows that Kmx equals 0 implies Kx equals 0. Finally, the eigenspaces of K asterisk span a dense subspace of H, since it contains the image under R of the corresponding space for A. The above arguments also imply that the eigenvectors for non-zero eigenvalues of K's in Hs all lie in the subspace H. Hilbert-Schmidt operators K with non-zero real eigenvalues lambda n satisfy the following identities. Proved by Kaleman, 1921. T R K 2 equals lambda n 2 det I minus z K 2 equals n equals 1 infinity 1 minus z lambda n 2 display style mathroom tr K caret 2 equals sum lambda underscore n caret 2 backslash det I z K caret 2 equals prod underscore n equals 1 caret inf d 1 z lambda underscore n caret 2 closing curly bracket closing curly bracket. Here TR is the trace-on-trace class operators and det is the Fredholm determinant. For symmetrizable Hilbert-Schmidt operators, the result states that the tracer determinant for K or K** is equal to the tracer determinant for A. For symmetrizable operators, the identities for K** can be proved by taking H0 to be the kernel of K** in whom the finite dimensional eigenspaces for the non-zero eigenvalues lambda m. Let Pn be the orthogonal projection onto the direct sum of whom with 0 mn. This subspace is left invariant by K**. Although the sum is not orthogonal, the restriction Pn K** Pn of K** is similar by a bounded operator, with bounded inverse to the diagonal operator on the orthogonal direct sum with the same eigenvalues. Thus, T R P N K P N 2 equals M equals 1 N lambda M 2 D I M H M D E T P N minus Z P N K P N 2 equals M equals 1 N 1 minus Z lambda M 2 D I M H M. Display style mathroom tr p underscore n k caret asterisk p underscore n caret 2 equals sum underscore m equals 1 caret n lambda underscore m caret 2 c dot mathroom dim h underscore m backslash mathroom det p underscore n z p underscore n k caret asterisk p underscore n caret 2 equals prod underscore m equals 1 caret n 1 z lambda underscore m caret 2 caret mathroom dim h underscore m closing curly bracket closing curly bracket. Since Pn K** Pn tends to K** in Hilbert-Schmidt norm, the identities for K** follow by passing to the limit as n tends to infinity. Notes. Kaleman. T. 1921. Zur Theorie der linearen Integral Gleichungen. Math. Z. 9. 196–217. DOI. 10.1007, BF 01279029. Dieudonné. J. 1969. Foundations of Modern Analysis. Pure and Applied Mathematics. Academic Press. Halmos. P. R. 1974. A Hilbert Space Problem Book. Graduate Texts in Mathematics. 19. Springer Verlag. ISBN 0-387-90090-X. Problem 82. Kellogg. Oliver Dimmen. 1929. Foundations of Potential Theory. Die Grundlagen der mathematischen Wissenschaften. 31. Springer Verlag. Carvinson. D. Putinar. M. Shapiro. H. S. 2007. Poincaré's Variational Problem in Potential Theory. Arch. Raschen. Mech. Anal. 185. 143–184. DOI. 10.1007 per seconds 00205 006 0045 1. Krein. M. G. 1998. Compact linear operators on functional spaces with two norms. Translated from 1947 Ukrainian article. Quote. Integral equations operator theory. 30. 140–162. DOI. 10.1007, BF 01238216. Landkopf. N. S. 1972. Foundations of Modern Potential Theory. Die Grundlagen und der mathematischen Wissenschaften. 180. Springer Verlag. Lax. Peter D. 1954. Symmetrizable Linear Transformations. Com. Pure APPL. Math. 7. 633–647. DOI. 10.1002, CPA. 3,160,070,403. Reid. William T. 1951. Symmetrizable Completely Continuous Linear Transformations in Hilbert Space. Duke Math. J. 18. 41–56. DOI. 10.1215 per second 0012-7094-51-018054. Zarnan, Adrian Cornelis. 1953. Linear Analysis. Measure and Integral. Banach and Hilbert Space. Linear Integral Equations. Interscience.